the precise definition of a limit, part 6. We're going to continue using the definition of the limit in order to prove that our limit is true. And we follow the same general steps, so you want to make sure you're stating the definition correctly and completely. And we also are still guessing a number for delta. The trick here is that we need to guess a number for delta. It can't be some sort of variable expression. It has to be a number. It's okay if this number is constant, so like delta is actually a number, it's a constant number. So things like delta are okay, and epsilon is also a number, so that's okay. But things like x, not going to work. And after we've found some sort of number for our delta, we'll be able to show that our delta works. So we have the limit as x approaches 2 of x squared plus 1 is equal to 5, and we want to prove that that is true using the precise definition of a limit. So first steps first, we need to state our precise definition of a limit correctly and completely. And I won't read it out for you this time. Once we've stated the precise definition of a limit, we want to show that that last part of it is true. So first, let's translate this. So this 2 is our a, the x value we're approaching. Our function f of x is x squared plus 1, and the limit we're approaching is 5. So we're trying to show in step 2 that if 0 is less than the absolute value of x minus a, so x minus 2 is less than delta, then the absolute value of f of x, so x squared plus 1 minus L, which is 5, is less than epsilon. And we want to show that this relationship is true no matter what we make epsilon. So we need to find a relationship between epsilon and delta. And we do that by taking this absolute value expression and transforming it into the one with delta, so that whatever's on the other side of our inequality symbol is a good guess for delta. So just like with linear functions, we start with some simplification and factoring. So we have x squared plus 1 minus 5, which simplifies to x squared minus 4. So we have the absolute value of x squared minus 4 is less than epsilon. This is a difference of squares, because x squared and 4 are both perfect squares, so we can factor this. So we have the absolute value of x plus 2 times x minus 2 is less than epsilon. And we can split this up so that we have the absolute value of x plus 2 times the absolute value of x minus 2 is less than epsilon. And we're trying to get to just having this absolute value of x minus 2 is less than something. And we could divide by this absolute value of x plus 2, but something weird will happen. We have a problem here. Delta has to be a number. If we divide both sides by this absolute value of x plus 2, which is okay because that'll be positive, it won't change our inequality, but we end up with an epsilon over the absolute value of x plus 2. This is not a number. So we need to figure out something else to do instead, because that x is a variable, so it can't be part of our guess for delta. Okay, so we need a little more room here. But we still have the absolute value of x plus 2 times the absolute value of x minus 2 is less than epsilon. Well, let's just try to get a number in here. So let's let the absolute value of x plus 2, this thing that we need to divide by so that we can isolate this absolute value of x minus 2, be less than some number k. We'll have to find an actual number to use later, but right now we're like, k is a number. It's less than this number. If it's less than that number, then we have the absolute value of x plus 2 times the absolute value of x minus 2 is going to be less than k times the absolute value of x minus 2. And that will be less than epsilon. Because k is greater than that absolute value of x plus 2. And that means that we can then divide all three parts of this by k. And when we divide all three parts of this by k, we end up with, on this right side of our absolute value inequality, the absolute value of x minus 2 is less than epsilon over k. And epsilon over k is a number, because we said that k is a number. That's how we defined it. So this is going to be a guess for our delta. But we still need to do a little bit more work because k is just a little too vague for us. So we need to show that there's some sort of actual number for k that will work. So we're going to do that by first making a guess. So guess number 1 for delta. And we're going to guess that delta is equal to 1. Now, you could use any number for delta for your first guess, but we just want to try to use something that is pretty easy to manipulate. Because we're just trying to show these bands, so figure out what kind of epsilon we could create from some sort of delta. So 1 is the easiest one. So we'll take a look at that 0 is less than the absolute value of x minus 2 is now less than 1 for delta. And then we'll take this, and instead of having an absolute value inequality, we'll have a compound inequality. And we're not going to worry about that 0 for now. So we have negative 1 is less than x minus 2 is less than 1. And what we're trying to do is we have the absolute value of x plus 2 is less than k. So we're going to try to take this and get this absolute value of x plus 2 so that we can try to get some sort of value for k. So in order to do that, well, instead of this minus 2, we want a plus 2, so we need to add 4 to each piece. So now we have 3 is less than x plus 2 is less than 5. And since this is positive, because we're greater than 3, this x plus 2 has to be greater than 3, which means it's also going to be greater than 0. When you have something that's positive, it will equal its absolute value. So x plus 2 will be equal to the absolute value of x plus 2 in this scenario. So we have 3 is less than the absolute value of x plus 2 is less than 5. So now we have an x plus 2 is less than something. So that means that we can let or choose k is equal to 5. And that should still make our relationship true. We'll just have to double check it first. Okay, so we just chose k is equal to 5 based on that relationship we found before. We know that it's possible for k to be equal to 5. So that means that now our delta being equal to epsilon over k is equal to epsilon over 5. And that's specific and a number, so that's going to be one of our guesses. But we also have to keep in mind that this k being equal to 5 came from a delta being equal to 1. So we can't have the delta being bigger than 1 or something weird happens. So we're going to guess that delta is equal to the minimum of 1 and epsilon over 5. So whichever one of these is smaller, we're taking to be delta. We already showed that this works out okay for 1, so now we just need to check for when delta is equal to that epsilon over 5. So we have 0 is less than the absolute value of x minus 2 is less than delta. And since we're really only trying to check this upper part of that, I'm going to drop the left side, because we're just worried about what's going on the right to prove the rest of our if-then statement, to show that this goes to epsilon. So now we have the absolute value of x minus 2 is less than, and we're testing delta is equal to epsilon over 5. And then we'll multiply both sides by 5. So we have 5 times the absolute value of x minus 2 is less than epsilon. And now we know that the absolute value of x plus 2 is less than k. And we also know that k is equal to 5. So this means that if we've shown this piece, then the absolute value of x minus 2, or sorry, x plus 2 times the absolute value of x minus 2 is less than 5 times the absolute value of x minus 2 is less than epsilon. And we're just trying to show that this piece is less than epsilon, so we can have that if-then statement. So we can ignore the middle piece here. And we have the absolute value of x plus 2 times the absolute value of x minus 2 is less than epsilon. And we can actually multiply those together. So we have the absolute value of x squared minus 4 is less than epsilon. And that is that simplified f of x minus L from the beginning. So we've shown that if this is true, when we choose this epsilon over 5, or, if epsilon over 5 is bigger than 1, if we choose 1, then we get our absolute value of f of x minus L is less than epsilon. So we've proven our precise definition of a limit. So that means that, yes, in fact, the limit as x approaches 2 of x squared plus 1 is equal to 5. Now we want to use the precise definition of a limit to show that the limit as x approaches negative 1 of x squared plus 3x plus 1 is equal to negative 1. The first thing we'll need to do is state the precise definition of a limit, which I won't read through in order to save some time, because these problems are a little bit long. Now we need to show that if-then statement at the end of the precise definition of a limit. So here our a is negative 1, our f of x is x squared plus 3x plus 1, and the limit we're approaching is negative 1. So we need to show that if 0 is less than the absolute value of x minus a, so that's x minus negative 1, is less than delta, then the absolute value of f of x minus L is less than epsilon. But we have our f of x and L. our f of x is this x squared plus 3x plus 1, and our L is -1. And we need to find a good guess for delta, so we will take this expression and make it look like this other expression. So let's just simplify that x minus -1 real quick. That'll be the same as the absolute value of x plus 1 is less than delta. So if we can get this right expression to look like the absolute value of x plus 1, then we should have a good guess for our delta. So let's do some scrap work here. So first we'll start by simplifying. So we have x squared plus 3x, and then plus 1 minus -1 gives us plus 2 is less than epsilon. And we can factor this, so we have the absolute value of the quantity x plus 2 times the quantity x plus 1 is less than epsilon. And we can split up these factors, so we have the absolute value of x plus 2 times the absolute value of x plus 1 is less than epsilon. And we want to solve for this absolute value of x plus 1. But we have a problem here. Delta needs to be a number. If we divide both sides by the absolute value of x plus 2, we don't have a number anymore. So epsilon over the absolute value of x plus 2 is not a number, because this x is variable. So we need some sort of constant number, not something that'll be changing. So it means we're going to have to find some k again. Now we can't divide by that absolute value of x plus 2, but we can let the absolute value of x plus 2 be less than k, which is some number. And if that happens, then the absolute value of x plus 2 times the absolute value of x plus 1 is less than k times the absolute value of x plus 1 is less than epsilon. And now we can divide by k. Why do my k's look so intense? And when we do that, on this right side, we end up with the absolute value of x plus 1 is less than epsilon over k. So we have a good guess for our delta. But k isn't quite specific enough, so we need to do some other guesswork in order to figure out some sort of good number to represent k. In order to find a nice number for k, one that'll make it so that delta is nice and small, we're going to start by guessing that delta is equal to 1. And we could guess that delta is equal to any small number, but delta equals 1 is something that's pretty easy to work with as we have to solve different things. And we know that we're trying to show this if-then statement, and part of that is this x minus -1 is less than delta. So we need to show this x plus 1 is less than 1 for our guess. So we can change this absolute value inequality into a compound inequality. So we have -1 is less than x plus 1 is less than 1. And now we want, instead of having an x plus 1, to have an x plus 2, because we're trying to figure out a value for k. So we want an absolute value of x plus 2 is less than something so that we can get a good guess for k. So in order to get this plus 1 to be a plus 2, we'll have to add 1 to each part of this inequality. So then we have 0 is less than x plus 2 is less than 2. And since x plus 2 is positive, that means, so let me make that blue again. So since we have this positive x plus 2, that means that x plus 2 is equal to the absolute value of x plus 2. So we have 0 is less than the absolute value of x plus 2 is less than 2. So a good guess for k, or a good choice for k rather, is 2. So we will choose k is equal to 2. So remember, we're trying to show that if 0 is less than the absolute value of x minus negative 1 is less than delta, then the absolute value of our function, x squared plus 3x plus 1, minus our limit, which is negative 1, is less than epsilon. And we've finally found some good guesses here. So we're going to guess that delta is equal to the minimum of 1 and epsilon over k, which we found was 2. And now our last step is to show that this is true. So we want to show that if delta is equal to the minimum of these two, that we can go from this statement to this statement. So we have our 0 is less than the absolute value of x minus negative 1 is less than delta. And we're trying to show that we can go from this to there with this delta. So let's simplify this a bit. So we have the absolute value of x plus 1 is less than our delta, which we're saying is e over 2. And then we can multiply both sides by 2. We're not too worried about this 0 because we're only trying to show this right side. So we'll multiply both sides by 2. So we have 2 times the absolute value of x plus 1 is less than epsilon. And now, since we know that the absolute value of x plus 2 is less than k, and that k is equal to 2, that means that the absolute value of x plus 2 times the absolute value of x plus 1 is less than 2 times the absolute value of x plus 1 is less than epsilon. So we don't have to worry about this middle part because we're just trying to show this being less than epsilon. So we have the absolute value of x plus 2 times the absolute value of x plus 1 is less than epsilon. And if we multiply that out, we get the absolute value of x squared plus 3x plus 2 is less than epsilon. And that's equivalent to the absolute value of x squared plus 3x plus 1 minus negative 1 is less than epsilon. So we've shown that we can go that if this is true for epsilon over 2, then this is true. So we've gone through our if-then statement, shown that it's true, that we can find a delta for every epsilon. So our limit statement is true as well.